Good afternoon, ladies and gentlemen. I hope you can all hear me. My name's Tommy White and I'm one of the developers of the MasterSeries. What I want to start off with is to welcome you all today. Now, the MasterSeries Building Design Suite. If we just have a quick look at the MasterSeries Building Design Suite, what is it? Well, it's an integrated system where you can import models from DXF, Revit, Tekla, AutoCAD. Obviously Tekla now, you will read the IFC format from that. And then we pull that into our modeling group, our master frame, our 3D model manager, a wind, and even another analysis option to do fine element. So that's the core of the model manager. And then we can exchange those back out again as GA drawings, or we can send them back out again back to Revit and Tekla and AutoCAD. Oh, sorry, rolling my mouse by mistake. So that's what we call the core. And then we have the design components underneath that, your steel design, your composite, your concrete, your timber, and your connection. And all of these 5 different design components are all optional. You only take what you need. So if you only do steel structures, take the steel and the connections possibly. And then finally, we can send that out also as DXF drafting, RC detailing as well, and scheduling for all your rebar. So what is the Building Design Suite? It's a single multi-material modeling environment for all types of structures. It's very versatile and handles anything from industrial type buildings to multi-stories and much more. It's not a vertical structure up and down. It can be anything you want. We have had people using it for obviously office blocks, shopping centres, grandstands, small school extensions, the whole lot. One of the nice things is it's all inside one environment. As we said, the steel, concrete, timber, timber, composite, all inside the one environment. Now, all the materials are seamlessly integrated into this one model. So it also uses one common style of design and is very, very powerful software, and naturally it all designs to the Eurocode BS or Eurocode. At a single click we can switch between the two. And then from a detailing point of view, we have bi-directional links with Revit, with Tekla, AutoCAD, Multi-Steel, DXF. And we can also produce these GA drawings and RC details as we mentioned. So what actual programs, because in essence, although I asked you who's using the Building Design Suite, it is in some respects a trick question, because the Building Design Suite is our way of bundling all our individual packages together in sensible groups so that you can come in and say, I want to do buildings and I want to do steelwork and I want to do concrete. No, I'm not interested in that or that, and it makes it easy. But in reality, what are we using? The master frame, the 3D model manager, and the wind are the 3 core programs, and you can, as an add-on, have the FEA analysis. Then the design is the steel, composite, concrete, and connections that we talked about. There's also the timber in there, a wee small program, and then the drafting and detailing is the master CAD for your BIM integration and the master RC for our scheduling. We also can export your data results out to Microsoft Office so you can have a system for people to read all your results without having to print any paper. So one model saves you time, no need to purchase separate systems for different types of buildings, and as I said earlier, it's modular and cost efficient. So I think I'm just going to get in, close this down, see what else I've got up here. I'm in the MasterSeries, but I want to start back from the MasterSeries. So I'm just going to load up Revit. in this case Revit 2015, and we've got a small-ish structure here that we can see on plan is pretty straightforward, and we can turn it around and look at it, and it's quite nice. So I'm going to export this out. We're not talking about how we do all this today. We're talking about just an overview of how we integrate the whole system together. So there are separate webinars that have been held on the details of the different aspects, like on BIM integration, like on steel design. We're just doing an overview today. So I'm going to create a unidirectional export, and I'm going to call it test RMS ABC, and I better give the other one the same name if you want. I'm going to select everything and send that out. So I'm sending that out. 219 frames exported, 81 columns, 2 materials, 54 different sections sizes, no floors because we didn't have floors defined in this model, and no errors, and I'll just close on that. So that's all I need to see from Revit. If I come into MasterSeries, we will see before we start that we are talking about version 2014-08 from the 29th of August. That's the most up-to-date version available there. So in the master frame, and we'll import a Revit link. These are all the different links that we can import to using the MasterCAD program. And I'm going to create a new model from a standalone. And there's my new ABC file, just created today at 1:10. And I'm going to say open. And I don't need any walls or slams, not that there actually were any in this case. And we're going to call it ABC, and we're going to extract everything. And we have 358 members, 191 nodes, and it's created the file, and I can just now come in and open up this file. So very quickly, let's have a look at this frame. As you can see, the different colors represent the different sections. We also have cellular beams. All this is steelwork, I believe. I don't think there's any concrete involved in this example, but that's okay. It's just a simple example to show you how easy it is to input the sections. And just while we're here, we quick histogram will tell us that all the different sections that came through. Built up sections with plates, nice. Flats, hollow sections, parallel flange channels, rectangular UBs, a cellular 356171, and all these different sections. So we're able very easily to import structures into Revit and analyze and design them, and we can send them back out at the end. So what I'm going to do is I'm not going to take this model and load it all up, because we don't really have time to do all that today in the next 44 minutes. So let's open an existing file I've been working with and playing with today, and I'm just going to go to, well, actually let's have a wee look first of all. Let's go to my favorites, and let's have a look at some of the structures that are done using the MasterSeries and the Building Designer Suite. These are typical frames that have been done using the MasterSeries, using the Building Designer Suite. And these are normally models that have been sent to us, usually because they want some tech support on them. I like this one. It's quite a nice wee school. 3 stories, little lean-tos, canopies and everything. I think that is another school of some sort. I assume that's flats by the look of it, and some sort of arena. So all different shapes and sizes of structures. Yes, there is a design of a building with trusses in it and purlins and everything in the model, transferring all the load for us. And it's been done very simply in the Building Designer. No need to worry about the hip end loads and stuff like that. So coming back, I'm going to pull in my example, which is this one, and I'm going to get this frame. So it's just loading in the frame, and the first thing we will notice is that this frame that I have looked at before and played with is got finer elements on it. It's got a transfer slab and it's got 2 shear cores. If I pull this up in 3D, we will see that we've got 2 shear cores. What we've actually got coming from the ground is a concrete sub with concrete columns, and then a concrete transfer slab, and then 2 shear cores, and then we have steel super frame on top, with the yellow members are the composite members. The green members, as I zoom in for you, the green members are our steelwork. The blue ones, just for a different referencing, are in fact the bracing members. We can see here we've got all these cellular beams. In fact, we'll also notice that I have slipped in here a beam with a plate welded to the bottom, and I think probably somewhere else we've got a plate girder. But also in the same structure, not just steel, concrete, composite, we've also got timber. So we've created some nice timber sections out the front here just to make the structure awkward for us. So this isn't really a structure. It was one that was given to us, but we've taken it and we've changed it around a bit just to make it more awkward and demonstrate more of the different features of the structure. So let's first of all look at, if we brought this frame in, the first thing we would probably do in the editor is to create some more members, add some members in, trim some members out, because it's no good just having a structural frame that could be brought in from Revit and then not changed. So in here, if we now go, the first thing I would have done would be to create views on the frames, so we can get layers at each level, but that's already been done for us. And I'm going to go into, say, level, I'm going to go into the roof. So here's my roof, and if I wanted to come along, I can easily just turn off the 3D to keep it nice and clean. I can easily say I want to add a new member, and you've got node points, so I could go and put a bracing member in there if I want to, and it clicks on it. I can easily say I want to go from the center point to the center point of that member, but obviously that wouldn't be right, so I would go from the center point there either to the center there or perpendicular, and I'm just going to do an undo there. I can also play real fun. If I wanted to, I could take this and I want to continue on up that member, along that member, which is 5.403 degrees approximately. So I'm running along that member, but I could also hover, wait for the intersection, and then suddenly I will have, as I come down, my intersection of the two for us. So I can hover over that node as well, just to make it easier. And there I've got this intersection of the two coming up for us. So I can do some really fancy stuff. Now the other thing I could do, if I just take those two hovers off, those two snap points, 1, 2, gone, hover over it and it's gone. Come on, go, that's you. Is I could say I want to hover, so I'm taking that member as a reference, and from here I want to go out. Somebody's turned. I want to do that member. There we go. And somehow, I'm just going to try that again. Not certain why I must have turned orthogonal on by mistake. No, I must have turned it on, because I should be able to just, there we go. I can say, right, running along that member, I want to go 2.55 meters. And it draws the member exactly. In fact, it was going backwards in my case. It went that way. My cursor was in the wrong place. So we have fantastic editing tools for you that make your life. So along that's it. 2.55. And there it goes. I was doing the first node rather than the second node because I was just talking too much. And naturally you can then come in and do an intersection there, and you could then come along and you could say, right, give me a perpendicular that's parallel to another member. That's orthogonal. That's perpendicular. And you have all these fantastic editing tools, but that again is not what we're about today. We're just giving you an overview of all the different facilities that we have. So I'm just going to do a couple of undos, get rid of extra nodes, and that should be me back to my model that I understand. So editing's fantastic. Sections, we have all the different properties. If we come into sections, section sizes, we can dead easy come along and look at any member and see that we can do steel sections. So if we just choose one of these members, here we go. This is a UB 203 133, and in fact, because it's on this top roof, it's actually a cranked member with two haunches at either end, because it's going to be cranked through this and haunched at either end to connect onto that. If we went to one of the more simple members, we could see this is just a UB. So what have we got? We've got the full range: UBs, UCs, RSJs, flats, IPEs, W sections. Now, if you're overseas, that's not a problem. We can import, or you can import, from a common delimited file your section properties. Very simple to do, and we can then come along and turn off these so we don't see the ones we don't want to see. At the minute, just for demonstration, I have every single last one that I have turned on. I can encase my member, so I can do a concrete encased member with a 1 by 1 millimeter encasement, which actually will give it the default of 50 mil all round. So it's a 152 with 260 by 1 by 255 casing and the concrete grade, and that will improve the design of that member. In a beam, it will improve its lateral torsional buckling. In a column, it will improve its compression strength as well. And I'll just turn off the casing. We also have, as we demonstrated earlier, this adding a section, plate underneath, plate above, channels. We can say what we want as a secondary section. We could put as a UB or a wee tiny UC underneath, so that it's now got a UB and a UC underneath each other. But I don't want to do that. We can say again do the castellated beams. So that's just the steel work. Plain beams, haunched, encased, compound, cellular, and finally built up, or even the ASBs. So you can build up your own plate girder with top and bottom flanges different sizes. And I'm just going to come back out here to the UBs. And what was that one? I'm just going to copy that back onto that section. So that's it, updated. We also have the concrete. We have concrete basically means any prismatic section. You can also do user sections for something that the program doesn't understand and bring in the section properties. So sections are very, very straightforward. Now, in the old days, loading was give me a member and what's the UDLs and what's the triangular loads, what's the point loads on it. Nowadays, that's not necessary. Good modern software allows you to do area loading, and that's what we can do. So if I come down to another level and just look at this level, say level 2, and look at this level, I can then come in and say, right, let's put some area loading defaults on. Maybe look at the full structure for this for the time being, full structure, and I can say that my roof loads are 0.45 with a 1.5 kilonewton live load, and that's actually just from lower, that's not the roof itself, we've ignored the roof, and then below that we've gone for different loading, and then for the basement we're going for a heavier load again. So we can modify our loads as per we want for each level of the structure. But obviously then we have to tell it how it spans and everything. So let's go in and have a wee quick look at area loading panel groups. Very quick whistle stop tour. Ground floor, second floor. The first floor is an FEA structure, so we don't put the area loading on the normal way. The FE looks after that. So if I go to level 2, here we go. I could turn around and say, no, I wanted to span that direction. Well, in fact, let's get rid of this altogether. So I'm going to delete that. Leave the definition, so I don't have to type the words in again. But now I'm going to go and apply. And I'm just going to go and apply it to all of those. And just check it's not in any of the rafters. So we just take out that one and that one, so it's not on the sloping rafters. So here we go, and we don't need it in here. This is a big opening area, and I don't like the way it's spanning, so I'm going to span it horizontally. Now I can span it shortest so that in each area we get our different areas of span, and more importantly I can override anything. So I'm going to go for the Z-axis spanning, and I'm then going to turn around and say, well, actually I just want to make some changes to this panel, and I'm going to make it change the span to Z-axis, X-axis, and I'm going to increase its dead load to 8 and its live load to 12. So in that little plant room, and I'm going to copy that to that as well. So those two members, those two panels, have increased loads and everything on them. Very straightforward. What else can we do? We can look at wall loads. He's got glazing around here, so he's not putting any glazing in these lovely corners, but everywhere else he's got these lovely wall loads. Has he any patch loads? Well, maybe not here, but let's see the full frame. He has no patches on the structure at this moment in time. I'm not going to put one on, I just want to save time, but we can put patches on the structure if we want. So that's our area loading on our different levels. So if we look at the structure as it stands, here we go, different levels. So the basement is 5.5, the second floor is 4.5, there's a wee bit of 16.5 in that area that had already been increased, and then the third floor is the same, and the roof is 0.25 and 0.6. Now, as a little tip for you, we did not define the roof as an area loading on the floors. And this is when we move into the next real smart part in wind analysis. So just turn this all off. Wind loading. Wind directions. We're going to look in 4 directions, and we'll have internal pressure and suction, and we're obviously working with the Eurocode values. What else can we do here? We can look at the wind loading cases, and we've just automatically said we'll have all of these cases, and we've got 84 loading cases automatically generated for us. Sorry, can I just check a second? I seem to be getting a noise on the line. Is anybody getting any noise? There seems to be a hissing noise on the line. I'm just going to mute myself. There, it's gone. I don't know why it was doing that, but we were getting a noise. I apologize for that. So we've got our wind directions, we've got our wind loading case values generated. What about the wind loading itself? Coming down through, let's find out where we're going to put this structure, right? We're going to locate it. In this case, I've said into Birmingham. So I'm going to say, let's go to Cambridge. So we're now in Cambridge, and I can say, well, actually, it's away down just there. And obviously, that's not very accurate. It's probably not going to make much difference in this case because the land around there is pretty similar. But if you want to be more accurate, you can go in and put in your national grid reference. Now, if you don't know your grid reference, but you know your postcode, there's quite a few good wee programs on the internet that will convert a postcode into a national grid reference. And we use the first 3 letter numbers and then the first 3 numbers in each direction of that grid reference. So we've now located our structure. We've also told it that the frame is rotated 34 degrees off the vertical for a north angle, and that's important because that allows us to use the standard directional method for our wind. And that's all I want to do in here. Very simple, just tell it where it is finally, and then we'll do some analysis and design. Wind panel generation. Well, before we do that, we just say which members are bracing, because the bracing members are the ones that aren't used to define the direction of span on panels, because we wouldn't want wind spanning from there to there and then from there to there. We want it just going straight across, ignoring that bracing member. So that's why we tell these members that they're bracing members. And then after that, we do go in to wind panel generation. So easy. Let's have a look at this frame. Now, on a frame like this, it will actually do most of it itself. It's very smart. And if I turn off that and just go for colors and draw all, there we go. There's all the panels. And the reason the roof is different out here to here is because this is a canopy. It's got wind on both sides. So it automatically, in fact, knew to handle that separately. Excuse me 1 second. So, how easy is it to do? Well, if I went in and killed them all, I've got no panels, and then just said automatically do them all. It's going to run around and look at this structure, and where it can, it will ascertain what the panels are. And there we go. What we don't have here is a panel down here for this opening, which we can go in and do ourselves. We can also take a panel and edit it in the same way. If you want to say, no, that is meant to be internal, or that is meant to be part of the, there is no canopy there, you can do that. So in our case, we can come along, add in one more panel, just zoom right down, and we're unable, just because of the nature of this little canopy. I'm just going to turn off the draw all, and what I'm going to do is I'm going to define this little panel in here, And it always helps if you get the right orientation. As you can see, we're starting to get this little panel. And once it starts on the panel, it doesn't like you selecting members that aren't on this plane. So there you go. That's that panel. All I need to do is say, no, 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 the wind is blowing from the other direction. So swap the direction of wind, and I can span it vertically or horizontally, and that's all you need to do. So that's all your wind analysis applied to the structure. Now add that with the fact that we've already told it directions you want to consider, and we end up with this fantastic system where we can see all the panels, and then we can see all the wind pressures on it. So we can see we're getting this high suction uplift on this panel. We're getting a bit of pressure here and a suction uplift. We're getting pressure here. Now I haven't finished this, so I will revert back to my previously saved model, which was completed. And the nice thing is it's done for all the different directions, and because we asked for it to be done for the internal pressures, it gives you the ones with this direction 0 degrees with internal pressure, so that it reduces that, but it increases this because it's blowing up and blowing out. And then you have the suction ones as well, so that it will increase this. And we can look at the values, and this is not a mistake. It is basically there is virtually nothing there. Obviously in this area you get very fine values, but you can see the 0.89 with the suction there. If we come back to P1, we get slightly different values, and then the W1 we get different values again. Now I'm going to come out of this. In fact, the last thing I haven't talked about really is the FEA, and then we will look at our design. Sounds like a tall order, but hopefully not. 5-10 minutes in each, 5 minutes hopefully in each will cover it. So let's look at our FEA. Sorry, excuse me. Here's our basic surface, and it's got no openings defined. It's got no edge supports. It's all supported just directly. The loading is the basic intensity of loading, and very, very simple for each surface. And if we look at the material and the thickness, it's a standard 300 slab with the standard reinforcement. So nothing special, it's very straightforward. Again, there's a very good webinar on FEA. So let's come back out, exit the editor, and I will not save because I've been playing around and I don't want to make mistakes. So very quickly, here's my structure. Coming back out, whoops, let's look at the full view. And let's analyze. And I'm just going to analyze a couple of the loading cases just for brevity today. I was analyzing just 10 cases. And it's going to take less than a minute to do them. Case 4, case 5, we're looking at this just down here in the bottom, 6, case 7, 8, and there we go. There's our analysis. So we can look at output. Obviously you've got all your tabular output as you would expect from a professional program. All your member forces, your nodal displacements, all that stuff is all there. You can get all those values for each case. You can look at the maximum values, the minimum values. So you could go to support reaction and say give me all serviceability maximum values, and that's all your reactions on your foundations. Graphical output, again very straightforward. Bending moments, obviously we will get some accentuation around the shear cores as one would expect, but this is the frame coming through with these big girders in here taking a lot of the load. and we can play around with deflected shapes and look at geometry, and oops, that's a bit scary. Coming back up to 1 to 1, that's a bit better. So deflect it with geometry, there's not much movement, there's nothing wrong with that frame. Bit of deflection there, but we'll see how it goes. Oh, wonder what that deflection is actually. Nodal deflections, y-axis, it's 122 millimeters. That's under dead plus live. Under live load only, it's 51. So 51 over that long span is probably an acceptable displacement. So I'm just going to come out of that. And now, before I go into my design, I'm just going to turn off the FE surfaces so that I don't see them all the time. So viewing options, FE, and don't draw mesh outside the editor. Okay, so we don't see the mesh area. It just makes it a lot clearer in the design. So design, what have we got? Steel design. Coming through, and we can look here at any of our members and we can see the design, and it's taking the worst case, loading case 6. And we can see all these members, and the reason all of these members are highlighted together is because we've set up what we call design groups. And if we look at our member groups very quickly, we can see that, for example, these roof members have been set into long span transfer rafters, and it said change the section, so it wants the same section size for all 8 of those. I think it is, yes it is 8. And for something else we've said no, we don't need to change. We're bracing, yes, we're going to keep it the same section size. If you look at, say, something like this, they aren't keeping the same section, so they will all be different sections, different sizes, depending on how they go. So we're able, using these member design groups, to preset how we want everything. So these beams are all fully restrained. These members here are 1L, but then they're restrained at every intersection. They're auto-restrained by the members coming into them. So that kind of makes sense. When we look at that in roof plan, that would be a sensible option to restrain it there, and there. So these are very useful, these viewing tools, the member design groups. So we were back here, we were looking at these, and we will see that if we design one, at the minute it's a 203 by 133. The roof loading isn't very heavy, to be honest, because it's very lightly loaded, and these are quite close together. We will see when we come into auto size, it'll actually auto size not just the one, but all of them. So if I was to come along, so 203 102 it says is the lightest. It thinks that's okay, the 178, but when I move into an inner beam, it's also using that 178, and one of these, this one, is not happy. So it's done all 8 beams to satisfy all the design checks together, and it's found that this baby is not happy under deflection. Now you could turn around and say, well, actually somebody's already set the deflection limit down to 200, so it's already relaxed that deflection limit down to 200 from 1/360 because it's a roof member. So I'm not going to mess around with that. I'm going to accept that. If we now look at some of our other members and go to full frame and go to vertical members. So if we just zoom in on one of these columns, I'm just going to take this column here, this run. So what we've got is a 203.60 and a 203.52 and a 203.52. So if I sized up this section and I just did that manually, I could come all the way down to 23 and it would work. But if I came here, it now doesn't work because those two members were tied together. It's, again, using this trick, we're able to say these two members are the same. size. So it now sizes it up so that both of these lifts have the same section size. And that's been applied all over here. So looking at the auto design, if I go auto design, I can actually say not just that member, but I want to design all visible members. So all of these columns will now be auto sized, and we'll find the top two lifts will be the same size for each of them, because they have to be the same section. So we're only going to splice below from here to here. Bear in mind this is a concrete column here. So this member is a 37 kilogram and that one's a 23, and this one also will be the 23. Likewise, as we saw here, 60, 52, 52. So it's again tying in and making rational decisions. Now these have been all by serial size. We can do this all by weight and ask it to auto do them again. And it'll not take long. And there we go. And now if you look at these ones, it's a 37 and a 23, but these ones here, well, that's the concrete one, it's a 60 and a 52. So it actually found a different section size that was lighter in reality. So we can do that on the whole frame if we wanted to. So we could just turn off the vertical filter and just ask it to go and auto size all the members and then reanalyze and redesign. Now if we looked at our roof, and I went through and did an auto design on the roof members just very quickly, they should design quite quickly. There we go. One of the nice things is that we can print out tables of members, so we don't print out all the design checks, so we can print out every page if you want. We can also go and we can just print out summaries. So if I go to print and I go print design output, and it's going to give me all the unity values for all those, and I could go and scan all those, but that's going to take a minute or two, so I'll just save time. So I can print out this table of all these fantastic summaries, and obviously that one isn't actually a real member, and print those so we can get a summary of the output. But what I can also do, and I can just cancel all this, is I can ask for unity values. So before I do that, I need to do something called scan for failure. So it's going to run around all these members and check if any of them have actually failed. And it's actually found one or two that have failed in our frame, because it's actually dealing with members that are outside our groupage here on the screen. And it's found 26 members that have failed. So, my text is a bit big. Font size, we'll go for Tahoma regular. That's a bit better. So I can see here that all these members have values of unity of 0.9 and 0.72 and 0.375 and 0.3, and they're all fine. I can even say only show me the ones that fail. Not scan the next failure, sorry, I apologize. There we go, only show the failing ones. So there's the ones that we didn't design, that need to be corrected, or the worst in each member size, or all of them, and you can print that out. So that's the steel design, very simple, very quick. Now I know I'm tight for time, but that doesn't really worry me too much. Just quick analysis. Because once you've seen one set of design, you can get a familiar idea from the next sets, and it is very, very straightforward. Here it comes, 5, 4, 3, 2, 1, and we are done. So let's look at the next design, concrete design. Going to come in very quickly, and I'm going to say no because I don't have any pad foundations in this structure. It's got rafts and things like that, and piles and whatever. So I'm going to view the full frame, and I'm going to look at my ground beam. So I can see my ground beams around here running along. Whoops. I should tell it not to design pad foundation. So if I just click here and say no pads, I just say OK, that'll stop it clicking. So I can look at a beam and I can see the reinforcement working pretty good on this beam. And I can see the reinforcement here on this with redistribution all working. And it's very straightforward. If you start to reduce your reinforcement by using your mouse, it will show you the failures as you design. But I can say make this all fail and then just say go on, you try it, and it comes back up with 8/12 is satisfactory at this location. So it's very straightforward and easy to use, and again we just need to run through with a design. We can also, if we want, take some bars out and then it'll automatically lap across here. If I use my lasso, I can take that lap and just put it nice and neatly in the middle of the structure somewhere smart and intelligent, and we're not using as many bars. So we have full access to the full reinforced concrete design in our frame. So we can then look at a column and we can see our columns. And in this case, what's the problem? We just need some more reinforcement, I believe. And I'm going to give you 4/16. Or I can say, keep it back down at 3, but make the corner ones 20s, 25s. So corner 25s will do, or it would have been 4/16 in the sides. So the choice is yours. The design is very straightforward, and you can ask it to go and design it itself. And it has attempted to design it, and what's it decided to ignore? It's very low overstressing on that, and it's decided, do you want to go that stage further, or are you happy? In my case, I'm going to say 25s. So we can design our beams, we can design our columns, everything in here. Now the flat slab area I will quickly look at the very end if I have time. So that's the concrete. Steel, concrete, what's next? We've done our steel work, so we might as well look at our connections. So integrating with the same frame, we can see that we have already come in here and we've chosen a beam, and we're looking at our fin plates. We can say yes, that will work, because quite often we get fabricators saying, we can't make these connections work. They're just not enough room to put all the bolts in that we need. So it's very useful, even if you're a consulting engineer, to have the ability to confirm that the connections will work. I mean, let's face it, you're going to have to design them in the end anyway, or check them, or approve them. And we can see here we have a bit of a problem because we're notching so much out of this shallow beam coming into the deep beam. Now, what can we do? Or should one say, first of all, what's our problem? Well, the notch stability is very unhappy, and the detailing depth is very unhappy. So we need to get a bit deeper plate. So, first of all, I would come along and I would say the minimum notch depth is 0. So that takes me right up in that depth, as close as I can go, 25 mil. And I'm going to do the same for the bottom, 25 mil. Now I don't think I can get the full depth in here. Depth of beam, 300's too much, 250, 260. What do we need to make that work? The overall notch stability is a problem as well because of it being unstiffened, so we would probably need to think about putting a deeper beam in here, or think about rectifying this to be a shallower beam and heavier so that it wouldn't have the same problem with the notching. Now, the other joints I did in this frame is a simple flexible end plate coming in staggered bolts, all checking out that it's okay, We can see here that we've just got one problem of detailing practice, and that is really to say that we're using a spacing of bolts that's not standard, but we're happy with those. We're going to accept that. And more importantly for you guys, one of the nice things we can do is all your base plates, and I can look at my base plate and see my results of my loading, and I can see, strangely enough, this was working earlier today. Did I save it? I'm going to go for 40 concrete and 40 grout. What's the problem? I think basically we probably just need to go for a bigger base. .400 by 400, and we're not getting any other, we're getting a pressure problem, and we just need to increase this to say 30 millimeters, and we could have probably brought it down to 400 by 400. So it's working structurally as long as you can get these bolts placed. These bolts are quite close. So very simple, full integration of steel and concrete, of connections. What's next? Composite design. Design composite and slim floor. Okay, can I get the viewing options up here? Yes. Just hide that FEA surface so I don't see it. And for composite, we're going to go straight to level 2. Or no, 3 is actually the higher level of composite design. And we can see our composite beams coming in. And let's have a wee look at the design here. And we can see this is with openings. And it's just doing a quick dimensional check on the openings. Openings here and here are too close to each other, so we would need to actually go in and fill in these openings because they're too close to each other. On this big beam that we're working with, remember we did this, it is a 305 with a plate. It's probably not going to work. It's well overstressed. I just put that in for demonstration purposes. If you wanted to make that work, we could ask it to try and do that for me, and it's just going to go a wee bit crazy and say that we actually need a 457191, and we probably don't actually need a bottom plate either. And we'll just take the thickness of that out. And it's fine without having to have the plate on the welded on the bottom. So we've designed that one. I think over here we had a plate girder, and again we're just getting some problems with the two openings that are too close to each other around these holes. So we'd need to go back into the master frame and actually fill in the openings, because you don't normally have an opening right beside a beam coming in, so you really should be filling in those two openings, or moving your openings about to actually make that work. This is just a whistle stop tour of it. As we can see, these openings aren't going to be very happy at all in this example. So I'm going to continue on here, and let me see, none of these are very happy, to be honest, because of all the openings. They just don't like it. If I went back down to my level 2, I didn't believe I had openings on level 2. So I can see that these are just failing no more with the transverse shear. So with the transverse shear, do we need to put in more mesh? and it's telling us I can't really do that. What about my studs? 1 per trough. 2 per trough makes it worse. Alternate makes it work, except for a little warning about but I don't have any openings. Oh, I do have openings, about the spacing of these openings for it being composite. So that's our composite design. Now, I did want to look at slim floor because slim floor is very similar, but slim floor is really specific for different for each geometry setup. Now, if I pull in the same model but with slim floor, I've created a different arrangement of beams on the 3rd level of this frame to mimic slim floor arrangements. So if I go into design, composite, yes, and then I go into level 3, I will see that I now have these slim floor beams defined as on-propped secondary slim floor beams, and they are working with plates on the bottom, a 10mm plate with a 75 projection, just to give you better seating. I can take the plate out altogether and see what happens, and in this case it will be happy without the plate, but we probably need it just for the construction, so I'm going to put that 10mm plate in. So very simply we can design these slim floor beams without much difficulty if we have the right configuration of spans on the frame. And finally, in the design components, timber. Not much to say about timber. If I go to full frame and I just choose one of these timber rafters, we'll see that it works. And obviously you would not think of cutting it down to be smaller for each rafter, so we will just stick with the one. We say it's one about 2% overstressed in there. We would have to either come along and choose a better grade of timber, C24, but our axial thrust coming through is still quite high, and we might need to go up and increase that section size as well to make that. It is internal, continuously used, and it is one piece, but it does have load sharing, which helps us a wee bit. But everything else we would need to make that a bigger section. So if I went 275, a bit extreme, 250, 260 would work if you got that section size. But again, it's very straightforward, and all we're demonstrating here is our ability to do timber inside the frames. I wouldn't necessarily dream of doing it in this sort of model, but you know, if it was to be timber, that's not a problem. So we have analyzed, we have designed. What we haven't done is output anything, and I'm going to go back out. Did I? Yeah, I just analyzed this again. It's a different model with the slim floor, but that doesn't matter. I can export this straight back out to Revit and bring it into Revit or IFC, 3D Plus, which I think is dead, Xsteel, which is Tekla's older format, StruCAD multi-steel. We can do a wireframe and solid, so we can export as a DXF wireframe, export, bring in AutoCAD. So we don't necessarily need to go to big stuff, the big Revit stuff, to get a 3D drawing of our structure. As long as we have the MasterCAD program, we can get information coming straight through into AutoCAD for us. and here it comes, and in this case it's a wireframe. Now the nice thing about this is that each layer is assigned to a color. Each color is a layer, a steel section size, so we can see all the different section sizes for use if we want. Now that's okay, but more important, I think, in the DXF area is the drafting area, where MasterCAD is very quick and useful. So if I come into MasterCAD and I produce a GA drawing, I'm just going to select my plan at level 3 and level 2, and I'm then going to move over to the page layout, and I'm going to choose the scale for this. Obviously 1 to 150, 1 to 125. I'm going to push it out to 1 to 100 and make that a knot and make them 1 to 100. So these are at 1 to 100. They could be at different scales. So what can I do? I can say, well, I want this to be stick outline, and I don't want center lines. I want my grid lines. I want my studs and my members and section labeled, and I want my shear forces at ultimate on all the beams. And in this one here, was that the one I was working with? That was the one I was working with. So the upper one, we could do similar, but we'll go for full output, and we'll have moment, shear, axial on beams, columns, inclines, at supports, and we will filter them so that we have only moments above 10, only shears above 75, and only axials above 50. Actually, the moments probably anything above 2 is more important, and we'll write it to 0 decimal places. And I'm going to export these two drawings straight into AutoCAD. It already exists, but I don't worry, I'm going to keep going. It's going to load up AutoCAD for me. And hopefully I will get 2 GA drawings. One wireframe, which makes more sense, and one 3D profile, which isn't quite as pretty, but demonstrates a use. So here we go. Oh, what have you just done to me, Mr. AutoCAD? There we go. I think Revit and AutoCAD were just getting a bit confused. There we go. So we can see for each of these beams, we're getting our section size and our grades. You're also getting your shearing forces on the members when they're significant. In this case, the shearing forces are in green as well, and I could turn around and say I want those to be in a different color, so I'm going to go for where's my shearing forces? There we go, shear forces. I'm going to change those from green to blue just so we can see the contrast, and we'll see them there, and we'll just close that back down again, and we can see, and naturally you can move them about and you don't need to put everything onto the same drawings at once. I've put your shear studs, your section sizes and your shearing forces on these, and one thing I might consider doing myself would be to go in and do a global search and replace to replace all the S355s. Now, sorry about that, I'm used to using the MasterSeries. Let's get that square again. If we come down and look at the other model, or up, we'll see that this is a wee bit more clunky in that it's got the members drawn in full profile on plan, which is a lot of extra lines and a lot of information we don't necessarily need. And you can see, even though we asked it for moment, shear and axial, only where we have moments does it actually give them to us. So here we have a moment of -35, but we have no moments here, or we have no moments that are above our threshold. I've just done that again. Naturally in here this is getting a wee bit cluttered, and you just have to go in, maybe take out a few of these and tidy up the structure. You can see here all the values coming through, and you can see the axial forces that you have in these members are a different value to the shear. So these are the tie members taking the axial, whereas these are the main members on the structure. So that's your GA drawings. The GA drawings get you a very good starter on the frame. We do not claim that it's going to be the be-all and end-all. Naturally, the other thing to be important is what's the drawing scale, what's the text height. If I look at this again very quickly, I think that I just got the titles. I think I was going to do labels at 2 mil. We can reduce that down to about 1.5 to get it a bit neater. So that's your GA. And just finally, what we should really do is to come back out of this and see what we can send out to Revit. So we can select our bracing members, or we can just go into the Revit Manager and export. This is a standalone file, and it's going to go into the master directory as Slim Floor Level 3. Export. Do you wish to export analysis results? I'm going to say no, and come back to Revit, and I'm going to take a new project, and hopefully I should be able. Oh yes, we're actually saving the name of the file first, as we're not actually looking for the import yet. Now it'll ask me for the import, and unidirectional, create a new model from a standalone exchange, and I believe I put it onto my standard MasterSeries directory, and that's my slim floor that I did today. And hopefully the date on that, well, it's not showing me the date, it thinks it's a music file for some reason. MSR must also be a music file of some sort. Open. I say yes. So it's bringing all my data in. And this is just trying to regenerate this frame for me. Here we come, and fingers crossed we might have something. So here we go, we're generating the frame, and just say OK and close this. And there's my model. So, ladies and gentlemen and all, I would like to thank you all for attending. Thank you and goodbye.